Okay, good morning, everybody. This tutorial is actually about a line of my work which I very seldom talk about. And recently, some visitors and postdocs in my group got interested in this subject. That's why I got my interest revived. I gave a shorter version of, actually not a shorter version, but a subset of this tutorial here at the Australian School of Information Theory the year before, and here I've added some recent results in this tutorial this time. So there are two parts in my tutorial. The first one is introduction to the I measure, which is a set-theoretic interpretation of Shannon's information measures, and I'm going to show you, the theory behind it and how we can use it to study different things, especially for Markov structures. And then the second part, it consists of discussion on something called full conditional mutual independence, which is a very special kind of Markov structure. But it turns out that the set-theoretic interpretation of Shannon's information measures is a very powerful tool for studying this kind of independent structure. And then this turns out to be a building block for Markov random field, and I also will discuss some of our latest results on characterizing subfield of Markov random fields, and also I'll talk about Markov chains and also some of our latest results on that. Okay, so this is the list of references for this talk. It's not very long. Okay, the first paper is a pioneering work by Hugo Ding, written in 1962. It is the first work that I know of that talks about the set-theoretic structure of Shannon's information measures formally. Okay, there were some works before which uses some Venn diagram type representations for Shannon's information measures, but this is the first work that treated the subject rigorously. Now, this work is in Russian. Actually, I have to thank Janusz about that, because I learned about this work from your book. Okay? And well, interestingly, I have made references to this work many times, but I cannot read the paper because it is in Russian. But I'll tell you an interesting story about this later. And then the second reference is my own work in 1991, which established a one-to-one correspondence between Shannon's information measures and set theory. And then there was the work by Kawabata and myself in 92 that talks about the special structure of a Markov chain. And then, we fast forward to 2002. Okay, there was a paper that we talk about the Shannon's the information theoretic structure of Markov random fields. And most recently, we wrote a paper on characterizations of Markov random field and subfield. So it looks like that I got interested in this subject every 10, 15 years or so. So next time I got interested in this subject may be after my retirement. Okay. And also, those of you who are interested in this subject can take a look at chapter 3 and chapter 12 of my book. So now about this paper in Russian. As I mentioned, I never have been able to read it, but recently I can. Not because I can now read Russian, but because Chao Chen, who is this guy here, is one of our former postdocs, he's very diligent in digging up literature, and he managed to find an English translation of the paper on the web. Okay, so this is the paper, and so there are very many interesting things in the papers which I did not know about. For example, some discussion on the Markov chain and things like that. Now, for some of you who may don't know, Hugo Ding is a legendary Chinese information theorist. In the 50s, he studied in Komogorov's group. He learned information theory from De Bruijn, and then he went back to China and started the whole school of information theory in China. So my collaborator, Zhen Zhang, and also some other active information theorists like Henri, Yeung, Xiang Xia, they all came from this school. Okay? So So in this pioneering work by Hu in 1962, he proved that for every information theoretic identity, there exists a corresponding set theoretic identity. So this is very nice work, okay? However, from my own point of view, this is not sufficient because what he says is that if you can find an information theoretic identity, you can find a set theoretic identity, which means that you can employ the tools in information theory to discover identities in set theory. But this is not what I want. I want it the other way, okay? Because there's a much richer set of tools in set theory than in information theory, which I would like to employ. And therefore, I came up with this idea of constructing something called the I measure. And with this construction, it makes it legitimate to actually operate all these Shannon's information measures in the set theory domain. And so in this first part of the talk, I'm going to describe to you the formal framework of the I measure, which actually is very simple in hindsight. So one thing that very few people know about is that the I measure actually was instrumental in the discovery of the first non-Shannon type inequalities. So it happened in the fall of 1995 that Zhenjiang came to CHK for a sabbatical leave, and we started working on non-Shannon type inequalities. We actually spent a whole lot of time on, working with these, four variable information diagrams. Okay, we spent a lot of time working on that. Although this is not necessarily the only way to look at the problem, but it did give a tremendous insight into the problem. Okay, so the introduction to the I measure. All right, so I think most people have seen pictures like this before. Okay, so here we have two random variables, x1 and x2, and we use a circle on the left-hand side to represent the variable x1, and a circle on the right-hand side to represent the variable x2. And in particular, okay, the area, you can think of it in terms of the area. The area of the left circle is identified as the entropy of x1. The area of the right circle is identified as the entropy of x2, and the area of the union is identified as the joint entropy of x1 and x2. This part is entropy of x1 given x2. This part is entropy of x2 given x1, and the intersection is identified as the mutual information between x1 and x2. Okay, that's very simple. Now, so how does this one-to-one correspondence work? Okay, this actually came from the work of Hugo Ding in 1962. So the one-to-one correspondence is that whenever you see H or I, well, in information theory, we like to distinguish entropy and mutual information, but mathematically, actually, there's not much of a distinction between the two. So either it's H or I, you write it, you replace it by mu star. I'm going to tell you what a mu star is. And so mu star is some signed measure or set additive function, which I'm going to tell you. Okay, when you see a comma, you replace it by union. When you see a semicolon, when you replace it by an intersection. When you see a conditioning bar, you replace it by set minus, where A minus B refers to A intersect B complement. So everything on the left-hand side is about information theory, and everything on the right-hand side is about set theory. Okay, examples. The first one, entropy of x1 is given x2 is equal to mu star x1 tilde minus x2 tilde. Okay, here it is an equivalence. Okay, it is not correspondence. It is equivalent to. Okay, I'm going to explain to you what it means. So mu star is is a set additive function that can be constructed, and x1 tilde is a set variable corresponding to the random variable x1. So if you look at the picture in the previous page, okay, so the set variable, actually correspond to this, the set variable representing this circle. Okay, because when I explain this to people, there's some confusion from time to time. Okay, likewise, entropy of x2 given x1 is equal to mu star x2 tilde minus x1 tilde, and the mutual information between x1 and x2 is equal to mu star of the intersection of x1 tilde and x2 tilde. just like that. All right, so as an example of the one-to-one correspondence, we have the inclusion-exclusion formula in set theory for any set additive function. Mu star x1 tilde union x2 tilde is equal to mu star x1 tilde plus mu star x2 tilde minus mu star x1 tilde intersect x2 tilde. Okay? And if you do this translation, it becomes the well-known identity in information theory. Okay? So I just go through this. Okay. All right, so this is how we construct the, this measure, this real measure mu star. So first we talk, we have a collection of n set variables, x1 tilde, x2 tilde, up to xn tilde, and we consider the field. Okay, for those of you who are not familiar with this terminology, the field is just the collection of sets that can be generated from this collection of n set variables by any sequence of usual set operations. There's anything you can talk about it. Okay, it is contained in this field, which we denote by script f of n. And the atoms in the field Fn are sets of the form, okay, intersection of yi from 1 up to n, where yi can be xi tilde or its complemented form. Okay. So as an example, the sets x1 and x2 generates the field F2, and there are 4 atoms in this field, namely this guy, this guy, this guy, and this guy. Okay. And there are a total of 2 to the power 4 equals 16 sets in F2, because each of these sets can be formed by some unions of these atoms, and there are 4 of them, and there are 2 to the power 4 such unions. Okay, so this is what I have to say about the field generated by x1, x2 up to xn. Okay, a real function mu defined on Fn is called a signed measure if it is set additive. Signed measure means that it doesn't have to be non-negative. Some atoms can take negative values. Okay, which means that for disjoint sets A and B in the field, mu A union B is equal to mu A plus mu B. And it is a consequence of the set additivity that the value of mu on the empty set is equal to 0, because for any, you just consider any set A, mu A is equal to mu A union empty set, which by set additivity is equal to mu A plus mu of the empty set. And by crossing out mu A, you find that the mu on the empty set is equal to 0. That's always the case for any set additive function. Okay, now here I talk about sign measure, which can take positive or negative values. The sign measure takes only positive values, and it is simply called a measure. Okay. All right, so here's another quick example. A sign measure on the F2 is completely specified by the values on the atoms. Okay, so if you tell me the values on these 4 atoms, then I can tell you it completely specifies the sign measure, because for any set in the field, for example, you want to know the value of mu on x1 tilde, you just write it as x1 tilde intersect x2 union x1 tilde intersect x2 complement. Okay. And then by set additivity, you get this, and we know the values of these things because they are the values of mu on the atoms. Okay? All right, so this is the construction of the I measure, mu star. So mu star is a specific sign measure. It's not just any sign measure. Okay? So in general, we let x tilde be a set corresponding to a random variable x, and we are going to fix n. It turns out that it is important to fix n. Okay? If you don't fix n, you cannot start the discussion. So we let the index set 1, 2 up to n be denoted by script n. Now this is a very special construction. We let the universal set be the union of all the xi tildes. Okay? And this means that if you consider the atom, which is the intersection of all the complements, okay, is equal to, by De Morgan's law, you can write this as the complement of the union of xi tilde without a complement. And this, by definition, is equal to omega, and the omega complement is equal to the empty set. Okay? So there's a special atom in the field. That's the atom consisting of all the intersection of all the sets is always equal to the empty set. And for this reason, we call the set of all other atoms the non-empty atoms. Okay? So this, well, because we're going to, most of the time we are going to ignore this empty atom, and we call this set A. We let this set A be the set of all the non-empty atoms, and this cardinality of this is equal to 2 to the power n minus 1, because we just take out the empty atom. So what it means is that the sign measure, under this special setup, a sign measure mu on Fn is completely specified by the values of mu on the atoms of A. Okay, these are all the non-empty atoms, because mu A0 always takes the value 0, as we explained before. The mu on the empty set is always equal to 0. So we don't have to talk about it. So what it means is that for n equals 2, okay, omega is equal to x1 tilde union x2 tilde, which means that this atom is empty. Okay, there's nothing outside the union of everything. And therefore, we can remove this, in this diagram, we can remove the rectangle that contains these circles. And so in this case, we only need to specify the value of mu on 3 atoms instead of 4 atoms. Okay. So as I mentioned before, the cardinality of A is equal to 2 to the power 2 minus 1, which is 3. Okay, so that's all I need to talk about this. Okay, so here's some very simple notations. We use G is some non-empty subsets of the set of all indices. Okay, xg now without a tilde, we are talking about random variables. Okay, x sub g is the collection of random variables xi, I, and g. X tilde g is the union of xi tilde I and g. Okay, and the construction of the I measure mu star is actually based on this theorem. Here I will use B to denote the xg tilde, where g is a non-empty subset of script n. Okay, so this is the union of some of the set variables, the set of all the unions of some of the set variables. So the claim here is that a sign measure mu on Fn is completely specified by mu b in script b, okay, which can be any set of real numbers. So previously we said that you want to specify a sign measure of Fn, you can specify the values of mu on the atoms. And here we say that you can specify mu star by specifying the values of mu on the unions. Okay, this is what this theorem is about. So, so one thing to note is that although not everybody will be convinced at this point, but I just want to mention that the size of A is equal to 2 to the power n minus 1. The same for the size of B. Okay, the size, the total number of non-empty unions of the set variables is also equal to 2 to the power n minus 1. So it turns out that it is just an invertible linear transformation of each other. Okay, that's why this theorem holds. A little bit more into the details.
It's the Möbius transform.
I'm sorry?
Möbius transform.
Well, yeah, exactly. Yeah.
We have to assume that the intersection of everything is empty here, or
the intersection of everything is no. The intersection of of all the complements are empty. Is empty.
Yes.
Yeah.
So you have to assume.
Yeah.
To get this.
This is yes. Otherwise, you have one more thing lying hanging around which you cannot determine. Okay. In fact, if you don't fix this, let's say we have this identity. For any set additive function, And without this construction, you cannot make sense out of this in the information theory domain because we don't know what it means. Okay. So that's why it's very important to fix n. If you don't fix n, you cannot put the n's together. Right? All right. So now this is actually taken from my book. Appendix 3a says that for any A in A, the set of non-empty atoms Fn, mu A can be expressed as a linear combination of the values of mu on the unions of xi. So it means that this is just repeating what I said. If the mu on any atom can be expressed as a linear combination of the values of mu on the unions. Okay, so now here we are also talking about something very elementary, and I have a puzzle. I've been very puzzled by the following observation, and so if you know the answer, please let me know. Okay, so we all know about this this identity for a set additive function. Okay, mu A union B is equal to mu A plus mu B minus mu A intersect B, mu A1 intersect A2. Okay. Now, if you move mu A1 intersect A2 to the left-hand side, okay, and then you move this guy to the right-hand side, you get this. Okay? Mu A1 intersect A2 equals mu A1 plus mu A2 minus mu A1 union A2. Okay, this is straightforward. Now, the interesting observation is that the second identity can be obtained from the first identity by exchanging the unions and the intersections. Well, for example, we see a union here, we replace it by an intersection here. You see an intersection here, we replace it by union here. Okay, maybe a coincidence, but actually, I think it's more than that. Okay, I don't know exactly why it is the case. This observation actually prevails in much more general context. Okay, so this is the first identity is actually a special case of the well-known inclusion-exclusion formula, which says that the mu on the unions is equal to summation on mu on the single sets, and then the minus the summation of mu on the intersection of two sets, so on and so forth. Okay, every time you have to flip the sign. Okay, so everybody knows that. Now, so this is the same thing. I just copied over. It turns out that you can prove a variation of the inclusion-exclusion formula. Okay, now here the new thing here is the B, but if you just forget about the minus B, okay, this formula can be obtained from the inclusion-exclusion formula by exchanging the unions and the intersections, okay, and the subtraction of B is just it's just trivial, okay. You just subtract B from every set involved, okay. So if someone can tell me why this is so, I mean, I would be very happy to know that. Okay? Why, for a set additive function, there may be some other examples that I don't know, but for all the examples that I know of, if it holds for a certain, if it holds for a set additive function by replacing the unions and intersections, you again obtain a valid identity. Okay.
So one point, I mean, on the top you can also do this minus B.
Yeah, you can.
Because
Yeah.
minus B will,
this is minor. Yeah.
Right. But
yes.
then I mean, how would you flip, minus to minus? Because one can be written as,
Maybe let's forget about the minus for the time being. Yeah. For this exchange thing, forget about the minor. Yeah.
No, but I mean, minus can be written as intersect and say something complement.
Okay. I think I need to be more precise when I say you can exchange the unions and intersections. I don't have a very good formulation for it yet. I mean, in fact, if you look at the original inclusion-exclusion formula, there's no involvement of complements. Okay, maybe we just restrict it to anything you like, and if you can somehow show this validity, within a certain context, I would be quite happy. Yeah. Okay, so this theorem says that there exists a unique sign measure defined on a field denoted by mu star, which is consistent with all Shannon's information measures. Okay, that's the mu star that you construct by taking the the linear transformation of the values of mu on all the unions. Okay, it turns out that this is consistent with all Shannon's information measures via the substitution of symbols that I talk about. Okay, and this sign measure is unique. All right, so because of this construction, we can formally regard Shannon's information measures for n random variables as the unique sign measure defined on Fn via the substitution of symbols. So instead of, so formally you can write, okay, it's equal to mu star x1 tilde intersect x2 tilde. Okay, it's not just a correspondent; it's equal. Okay, by writing an equal sign, you can do anything you like on in a set domain. Right?
When you say unique, it is unique for each joint distribution.
For each joint distribution, yes. Okay, and because of this, we can, as I mentioned, we can employ set-theoretic tools to manipulate expressions of Shannon's information measures. And but one thing to note is that mu star can be negative. Okay, that's something we have to pay attention to. It's not a fault, but it is something that we have to pay attention to. Okay, so for n equals 2, mu star is always non-negative, and for n equals 3, mu star is not always non-negative because this thing, which is the intersection of the 3 set variables, may be negative, as I'm going to explain. Right? So for 2 variables, the 3 atoms are these 3, and the 3 atoms are all the mu star on all of these 3 atoms are all Shannon's information measures, which are always non-negative. Specifically, this guy is conditional entropy, which is non-negative. This is mutual information, non-negative, and this is again is conditional entropy, non-negative. Okay, so therefore, mu star is always non-negative for 2 variables. For 3 variables, okay, there's 3 different types of atoms. The first one is this one, which is the conditional entropy of one variable given the other 2. It's non-negative. Okay, same thing for this guy and this guy. Okay. And then for these type, the second type, it is a mutual information between 2 variables given the third one. Again, it's non-negative. However, this guy in the middle does not correspond to any Shannon's information measure. So it's not clear whether it is always non-negative or not. And it turns out that it can be negative. Okay, the construction is this one. So we start with 2 binary random variables x1 and x2, and which are independent of each other. And so x1, x2, these are just independent fair bits. And then we just take x3 equals x1 plus x2 modulo 2. Okay? And then it's a well-known example that for this construction, x1, x2, and x3 are pairwise independent. Okay? And as you can check in this diagram, okay, I just give you the answer here, okay, but you can check. So the mutual information between x1 and x2 is equal to the sum of these 2 guys, which is equal to 0. The same thing for the mutual information between x2 and x3, and the mutual information between x1 and x3. Okay? And also you can check that given any 2 variables, the third variable is deterministic. And that's why the conditional entropy of x1 given x2 and x3 is equal to 0. The same thing for these 2 zeros here. However, this is not the 3 variables are not mutually independent. Okay? And in fact, this is the right I measure describing these 3 random variables. And it turns out that this guy in the middle is just negative. Okay? It's just the way it is. Okay? All right, so next I'll talk about information diagrams.
Yes. Is there some operational meaning of this quantity?
That's set-theoretic operational meaning, but
information theory.
not.
The others have
Yeah, not that I know of. In fact, I have an example about this guy in the middle being equal to 0, but it does not correspond to anything that I can think of. I just use a computer to crunch out some numbers. The numbers look pretty random. It doesn't correspond to any Markov structure whatsoever, and that this guy in the middle can be 0. So I have no idea.
But I mean, it's just mutual information minus conditional
Yeah.
mutual information,
Yes.
right? So
Yes.
that's what it is.
Right.
It should
Right.
be, positive or negative.
Yeah, but even when it is 0, it's not clear what the meaning is. Okay. but nevertheless, it is still very useful. Okay. All right, so let's take a look at this 3-variable information diagram. Okay, as mentioned before, it's just the same diagram as I talked about before. And one thing to pay attention to is that the middle guy can be negative, right? All the other atoms must take a non-negative value. Now, for 4 random variables, actually, this is something interesting. I learned this drawing from a Taiwanese mathematician visiting our group like 15, 20 years ago. Before that, I was, the canonical way to construct a Venn diagram is the following. So for 2 variables, you can do it in 1 dimension. Okay, I use this line to denote x1 tilde, and use this line to denote x2 tilde, and this is the intersection. Okay, and for 3 variables, we can use 3 circles. Well, so what you do is that you just expand a line into a circle, and then you add in another circle. Okay, and then you can still manage to do this in 2 dimensions. This 1 dimension, 2 dimensions. So when it comes to 4 variables, the canonical way to do it is like this. You have 3 ice cream scoops, okay, like a sphere, so you intersect them like this way. Okay, you just expand it into 3 dimensions, and on top of that you put in another ice cream scoop. Okay, that's the canonical way. But it's very difficult to visualize. Okay, and so now this the beauty of this construction of the diagram is that when you so we have the 3 circles to start with. X1, x2, and x3, and then we put in a kidney shape for x4. Okay, so the first thing to do is that we check that they are exactly 2 to the power 4 minus 1 equals 15 on empty atoms in this diagram. Okay, and the reason why this is a valid construction is because this kidney shape actually splits each non-empty atom in F3 into 2 non-empty atoms in F4. For example, this atom x1 tilde complement intersect x2 tilde minus intersect x3 tilde complement correspond to this guy here. Okay, this guy. Okay, this is an atom in F3, and now this kidney shape, split it into 2 atoms. Namely, this part is in x4 and this part is not in x4. Okay? So by drawing the line like this, you manage to split every atoms into 2 in 1 stroke. Okay? And then also there is the extra atom, which is only in x4 but not in the other in the other set variables. Okay? So this is a valid representation, and which can be better visualized. Okay? Than doing it in 3 dimensions. Okay, and I also learned about another representation from Tariq. Okay, this is also a very neat way to construct it. You just draw x1 like this, x2 like this, x3 and x4 like that. Okay, so it also works. But I'm more used to the other kidney shape diagram. Okay, now the next theorem says that if there's no constraint on the n variables involved, okay, then mu star can take any set of non-negative values on the non-empty atoms of the field. which means the following. Suppose I have a 3-variable diagram, and I just arbitrarily put in non-negative values on the atoms, and I ask whether I can construct a joint distribution for x1, x2, and x3 such that the mu star looks like that. Okay. It turns out to be rather easy. So what you have to do is to consider mutually independent random variables, capital A, B up to G, that corresponds to these non-negative values A, B, and G. Okay. And you let A be the collection A, B, C, D, which corresponds to these 4 atoms in the set A, in the set X. Okay. So A has entropy equal to small a. Okay. B has entropy equal to small b, so on and so forth. So A, you let X be that, Y be this, okay, and Z be this, and it can be shown that with this construction, you actually get mu star exactly equal to this. Okay, so this turns out to be a very important observation. So any non-negative numbers you put on the atoms, you can realize it. Okay. Okay, now it's something interesting. So now in general, if you go beyond four random variables, it's pretty hard. Yes, sorry.
Just a question on the previous slide. So how about if you have negative numbers?
Then it may not be realizable.
Oh,
Okay.
do we
But,
know when, or?
well, I mean, if you have negative values, you can violate Shannon's the Shannon type inequalities. Then you're gone. Okay. But for non-negative values, it can always be realized. Okay. Yeah.
What do you call the inner bound? What do you name the inner bound from requiring these to be greater than or equal to? Boolean or something?
I don't have a name for that. I don't have a name for that.
Boolean polymerase?
Whatever.
Don't have a name.
I don't have a name for it.
Is it even interesting to study these kind of, like, what conditions on these non-negative numbers?
I mean, this is exactly. I mean, the study of this is exactly the study of the entropy inequalities. Yeah.
On Tuesday, Professor Shannon introduced a full-rank Hom to n-dimensional rank Hom. Actually, the scatter results is equivalent.
Yeah, these guys are, just keep in mind that these guys are just nothing but a linear transformation of the joint entropies. But it turns out to be extremely useful because there's a set-theoretic structure in it. Okay. Okay, now as I mentioned, if you go beyond 4 random variables, it's terribly difficult to visualize the information diagram. Okay, I have seen constructions of Venn diagrams for any random variables on 2 dimensions, but I think, although you can do it, but it's close to useless because it's very hard to read them. Now, however, it turns out that if these random variables form a Markov chain, the structure of mu star is much simpler, and the information diagram can always be expressed in 2 dimensions. So let's take a look at the simplest example of n equals 3. Okay. We have this Markov chain x1, x2, and x3, and even only if mutual information between x1 and x3 given x2 is equal to 0. Or, in set-theoretic terms, mu star x1 tilde intersect x3 tilde minus x2 tilde is equal to 0. Okay? So, because the value of mu star on this atom always vanishes, we can suppress it in the information diagram. Okay, we don't have to show it. Okay, so this is how it works. So we are talking about, for the Markov chain, we are talking about this guy always taking the value 0. Okay, so to suppress this atom, you only need to show the top part of the picture. Okay, and then a better way to show this, which I learned from Karl Barter, is to draw 3 mountains in a row. Okay. And Okay, let's do a sanity check. Now, in this information diagram, mutual information between x1 and x3 given x2, which is an intersection of this and this, minus this. So you get nothing, okay? It's actually equal to mu star on the empty set, which is equal to 0. Okay? So this corresponds to the Markov chain. Okay? And also, another thing to note is that this guy, which is potentially problematic, which is the intersection of 3 sets. Okay? Now, the intersection of x1, x2, and x3 turns out to be equal to the intersection of x1 and x3. Okay? And this the intersection of two things, and so this is a mutual information, and so it's non-negative. Okay? So we see very easily that for a length 3 Markov chain, the mu star is actually a measure, okay, which always takes non-negative values. Now, it turns out that this theme can be generalized to a Markov chain of any length. I'm not going to get into the general case yet, but let's do a checking for the n equals 4 case. So for n equals 4, we have this Markov chain, and it turns out that mu star vanishes on the following 5 atoms. Okay, and the information diagram can be displayed in the 2 dimensions in the way you would imagine. And also that the value, okay, so mu star vanishes on these 5 guys, and there are 10 more atoms, and it turns out that for the remaining atoms, the value of mu star corresponds to Shannon's information measures and hence are non-negative. So again, mu star is a measure. Okay. So this is the information diagram for 4 variables. Now, okay, this is about the non-negativity part of mu star for the length 4 Markov chain. So it can be shown that the mu star always vanishes on these 5 atoms, and so we suppress these atoms, and then we can obtain this information diagram. Okay, you can check this, check the validity of this representation. Okay, and okay, so it is for this case, when we have a small number of variables, it can readily be checked actually in the diagram. Okay, that for the remaining 10 atoms, they all correspond to some Shannon's information measures. Okay, so on these remaining 10 atoms here, mu star on them correspond to these Shannon information measures, and hence they are non-negative. Okay? And therefore, mu star is a measure. Okay? So I'm not going to explain this phenomenon in full generality at this point. Rather, I will go for a more general framework, and then I will specialize that into this Markov chain and explain to you why this is the case. Okay? Okay, so for a general n, this is the picture. This is the right picture, and it also happens that mu star is always non-negative. Okay, so this is something that we have to keep in mind for the rest of this tutorial. Okay, so we are going to discuss this in the context of a Markov random field. Now, some applications of information diagrams. The first illustration is the data processing theorem, which is very well known. If you have a Markov chain like this, x, y, z, t, then the mutual information between x and t, which are the 2 variables on the side, is always upper bounded by the mutual information between the 2 variables in the middle. Okay? So in terms of the information diagram, this is very clear. So ixt is this atom here, intersection between x and t. Okay? And iyz is the intersection between y and z, which are these 4 atoms. Okay? And in fact, we can write down immediately that iyz is equal to these 4 atoms here. And because mu star is non-negative, we can see right away that this is greater than or equal to this. Okay? Because all these three guys are non-negative. Okay? All right, so this finishes the first part of my tutorial. Should we take a break here?
Yes.
Okay.